Announce this driver assistance systems regular session. My name is Gerd Wannelik. I'm from Chemnitz University of Technology, and we have two splitted parts. So one is on human factors, that are the first two papers, and then two technical papers are presented. The first one is from Nelly Osharova and from Robert Bosch, and she is talking about effectiveness of forward collision warnings of different driver attention states. Please.
So, good morning, ladies and gentlemen. I welcome you to my presentation today. I'm going to talk about a study about the effectiveness of forward collision warnings for different driver attention states. This study was performed last year in a cooperation between Bosch and the Karlsruhe Institute of Technology. I don't want to bother you with statistics, but every year more than 4,000 people die in road traffic fatalities in Germany. Even much higher is the number of accidents with casualties, which was 2009 more than 300,000 people. The second largest collision type after intersection collisions are rear-end crashes, and one of the main reasons for rear-end collision is the driver's inattentiveness, according to studies. So collision warning systems have the aim to help the driver to prevent or mitigate collision in such situation. The challenge nowadays is still to convey the same urgency and to obtain high effectiveness for attentive and inattentive driver at the same time. One approach which I'm going to introduce today is an adaptive collision warning system which uses for the first time the driver attentiveness in order to adapt the human-machine interface. On the basis of sensor data which is provided to the warning system, the criticality can be determined, and with the help of attentiveness monitoring of the driver state can be determined, and assumption about the expected driver reaction can be made. So on the basis of this input, the adaptive warning system is triggering two different or more different strategies for attentive and inattentive drivers. The target for this system is to increase the benefit and the acceptance of the common collision warning systems. In order to select appropriate HMI concepts, we derive several requirements which the selected warning should fulfill. These requirements were based on state-of-the-art, and one of the requirements are that the warning should attract the driver's attention to the dangerous situation and generate a collision mitigating driver reaction. Furthermore, it should possess a minimum of intensity, be multimodal, and have an appropriate warning point in time. Additionally, it should be compatible to the critical event and be not too complex and consistent with other indicator signals. And finally, which is most important, the warning should be accepted by the driver. On the basis of these requirements, we selected several visual acoustical warnings which have already been evaluated for at least one driver state, that means for attentive or inattentive driver. And which is the most important for this adaptive warning, collision warning system is the interaction of the driver in both attentiveness states with those HMIs. So therefore we performed a study to investigate the driver behavior with those selected HMIs in a fixed space simulator. This investigation was carried out in 2 stages. The first stage had the focus on the acoustical warning, and the second one on the visual, but in both of the stages we were warning multimodally, that means visual acoustical. Here are some further information about the study. In the study, 58 participants took part. Each of the participants completed 2 drives. In the first drive, the participant was driving inattentively, and in the second one, attentive. For the systematic distraction of the driver, we designed a secondary task, which was a navigation instruction. This navigation instruction was mounted to the right of the driver at the height of the passenger seat. And during the drive, the supervisor was asking questions about this navigation instruction. The driver was then forced to take his eyes off of the road and to answer the required instruction. One of the most frequent rear-end crash scenarios happened driving ahead following a vehicle which suddenly brakes. Scenario was designed for our study on a 3-lane highway. Both vehicles were driving in the middle lane of the street with a constant speed of about 19 kilometers per hour. Each participant was additionally instructed to keep a distance at about 40 meters to the leading vehicle. Once the supervisor was sure the required driver state was achieved, the critical situation was then manually triggered by the supervisor, and at this moment the leading vehicle performed emergency braking. So, as already mentioned, we carry out our study in 2 stages. The first stage had the target to determine an acoustical HMI which provokes short reaction times for both driver states at the same time. We selected 5 different signals. The first 2 were ear cons. Ear cons are signals which are synthetic tones, which all of you know in your vehicles, in your cars. And the drawback of these signals is that they don't provide directly the required action. That means you have to train at first what you will associate with this signal. The difference between alarm 1 and alarm 2 was the intention of the signal and its length. The third signal was an auditory icon. Auditory icons are environmental signals. For an example, a car horn or a tire scratching, which was used in this study. And the next one is a new type of tone that's called hyricon, and it's a combination between earcon and auditory icon. The last one we used is speech message. You probably all know from infotainment or navigation systems, and the one we used here was the word break, which was pronounced by a voicemail in this study. So with those 5 signals, we used 5 test groups. Each of them was driving with one of those signals. And additionally to the acoustical warnings, the participant received also a visual warning, which was displayed in a head-up display. We had also a baseline. The baseline was the control group, which was driving without an acoustical warning. That means they received only a visual warning in this case. So let us have a look at the results for inattentive driver state. You can see in the plot that both earcons, alarm 1 and alarm 2, involved very large reaction times with very large variance, which is probably because of the incomprehension of the tone. The reason for the long reaction times of the auditory icons are diverse. We asked our participants after the study what they actually associated with those signals, and about the auditory icon they said that they not only associated the braking of the leading vehicle but also its acceleration. Additionally, this signal provides no direction cues. That means that we should take into consideration that a driver could associate the braking of with another traffic participant. The large reaction times of the Hybricon are because of the combination of this type of tone of an iacon and an auditory icon and an iacon. And the only signal which showed an indicative reduction of the reaction times was the speech message, surprisingly. An additional investigation was performed with the both best two tones, which were the speech message and alarm 2, and they were compared to the control group. And as you can see, and a statistical test showed that the reaction time can be indicative reduced by a speech message, by acoustical warning. So therefore, we can summarize that an acoustical warning with a clear message can and is necessary to guide the driver's attentiveness to the imminent air danger. For attentive driver state, the results are pretty different. You can see in the plot that there is actually no significant reduction of the reaction times. Only alarm 1 and alarm 2, the two earcon signals, showed slight but not significant reduction of the reaction time, which is probably affected by the experiment setup in the second drive. So considering the results of stage 1, we moved to stage 2, which target was the determination of a visual HMI, which provoked short reaction times for both driver states again. And we selected 4 signals, which are displayed here in this slide. You can see the first one, a visual, was a warning triangle, which is a common use signal in our nowadays driver assistance systems. The second one was a brake bar, the next one was a brake light, and the last one was collision notification. All of those visual warnings were displayed in a head-up display with a blinking frequency. Additionally to those visual warnings, the test groups or the participants became also in inattentive driver state the speech message from stage 1, and in attentive driver state they received only the visual warning. So the results for inattentive driver state, you can see in the plot that the warning triangle and the brake bar showed a slight but not significant reduction of the reaction times. However, the brake light and the collision notification increased slightly but not significant the reaction time, which are the causes I'm going to discuss in the next slide. But summarizing, no additional reaction time could be observed for inattentive driver state. However, an intuitive and simple visual warning could serve to affirm the audible warning. For attentive driver state, you can see the results are pretty different. Surprisingly, the warning triangle involved very long reaction times here, which are maybe caused because of the ambiguity of the signal and its unclear message for this situation. the brake light, just the same like in inattentive driver state, showed short reaction times which were not significant, but it also has large variance, which is probably because of the message of the signal. Brake light is common known signal which provides an information about the braking of a leading vehicle, but it provides no information about the emergency of the situation, which is probably the cause for those variants here. The collision notification compared to the control group showed no significant reduction. However, compared to a simple visual warning like the brake bar, we observed significant reduction of the reaction time, and therefore it can be compared, it can be confirmed that complex visual warning can involve large information processing times, which are resultant in the long reaction times here. The only visual warning which showed a reduction of the significant reduction of the reaction time was the brake bar, and therefore we can state that simple and intuitive visual warning with a clear message can reduce the reaction time of attentive drivers. At the end of my presentation, I would like to summarize the highlights of my presentation. An acoustical warning with a clear message can reduce the reaction times of inattentive drivers. For attentive drivers, a simple and intuitive visual warning is important in order to reduce the reaction time significantly. In this presentation, you could see that not only the driver's attentiveness is important in order to mitigate a collision, but also the used cues to communicate to the driver. That means the provided HMI to the driver is important in order to increase or to mitigate a collision. So therefore, an adaptation of warning intensity and modalities to the driver's attention can be useful to increase the benefit and the customer's acceptance of collision warning systems. Thank you very much for your attention.
So we have time for 2 short questions. So if there is no one, I have one. So how did you pre-select the acoustic tones and also the signs? So there is a large amount of possibilities.
We tried on the basis of the requirements and showed to select acoustical visual warnings which have already been evaluated for at least one driver state. And it was important for our collision warning system, it was important to have a high benefit for both of those driver states.
So, is there
I have a question about your control groups, the participants in the visual warning and audio warning. Were they different or were they the same group?
Sorry, I don't get it.
I'm here.
Yeah.
The participants in the testing that you did for the visual warning and the audio warning, were they different or were they the same group of people?
They were different.
I'm wondering, why did you choose to do with different group of people? I mean, if you have chosen to work with the same group, I mean, you could have the comparison would have been better, or you could also subjective comparison of the 2 methods. I mean, why did you decide to choose different groups of people?
Because of the, when you once have seen this situation, you are already prepared for the situation. So therefore we selected two different groups.
Okay, thank you.
Okay, thank you again. So we go now over to the second talk, and the title is An Approach to Automotive ECG Measurement Validations Using a Kind-Degraded Test Framework. And the talk is given by Johannes Schneider from the FZI Research Center of Information Technology in Karlsruhe.
Welcome you to my talk. The topic of our paper is an approach to automotive ECG measurement validation using a car-integrated test framework. In the next 15 minutes, I want to present you a framework that allows us the validation of our capacitive ECG measurement and other physiological sensors under real driving conditions. First, an overview of my presentation. I will begin with the motivation and explain why it can be helpful to use physiological sensors in future cars. Then I explain some background about ECG measurement and the capacitive ECG measurement. After this, I present our car-integrated test framework and close my talk with our results and a short conclusion. In Germany, we have a yearly average of 100,000 people that are injured and 4,000 people that are killed in traffic accidents. Of course, this causes very high socioeconomic costs. In the year 2009, the costs reach about 35 billion euros. As you know, the main reason for traffic accidents is still human failure. Today, people have high workloads and stress in daily life, what could lead to drowsiness or even microsleeps during driving. Also, it can be that some people are distracted or have reduced alertness because they are overwhelmed by the complexity of traffic. What we want to do is to assess the driver's cognitive or emotional state with physiological sensors and provide this information for future driver assistance systems. Many works show that the physiological data like heart rate, skin conductivity, or peripheral temperature are closely correlated to the cognitive or emotional state. For example, skin conductivity and heart rate metrics are closely correlated to its stress level. Another example is that heart rate and peripheral temperature is closely correlated with drowsiness. In our work, we focused on ECG measurement. I'm not sure if everybody of you is familiar with ECG. It's a measurement of the electrical activity of the heart. In the picture, you can see the well-known ECG signal. You can also see the so-called R peaks. The detection of the R peaks allows the calculation of the heart rate or the heart rate variability. In the last years, we do researches in capacitive ECG measurement. Capacitive means that you don't have to wear electrodes on your skin. We design special electrodes and special analog front ends that can measure the ECG even through closes. This gives us many possibilities. We are now able to integrate unobtrusive electrodes into driver seats, for example. One problem is that relative movements of the driver versus the electrodes causes artifacts in the ECG signal. So our idea is to use driving dynamics data to estimate the signal quality. So what we would want to do in future cars shows this slide. We want to measure physiological data with our unobtrusive sensors, do some signal processing to assess the driver's state, and provide information for assistance systems, which in the next step can then support the driver. The problems are we want to use unobtrusive sensors. So if you can buy the sensor, we have to develop them, and we need a possibility to validate the measurements by reference device. As mentioned, we also want to use a driving dynamics data to estimate the signal quality. In the next step, we want to develop algorithms for signal processing. For example, algorithms that assess the driver's state or algorithms that estimate the signal quality. For this, we need a possibility to do test runs, gather data, develop the algorithms offline, and then test them and integrate them online. This is what our test framework allows us to do. So in conclusion, what were our specific goals? We wanted to create a platform for evaluation verification of physiological sensors and algorithms under realistic driving conditions. With this platform, we want to test the capacitive ECG measurement and validate the measurements by a reference device. Furthermore, we want to analyze the influence of vehicle dynamics on the signal quality of the ECG, of the capacitive ECG. Here you can see our test car. It's an instrument Audi Q5. The car is equipped with many sensors and actuators, for example, steering, braking actuators, electronic throttle, multiple cameras, EMU, and GPS. I think I cannot impress you. We can control actuators and receive data from the sensors via CAN bus. For the ECG measurement, we integrated special textile electrodes into the driver's seat. This slide shows the hardware we used. On the one hand, we have a custom embedded system for capacitive ECG measurement. The system acquires and digitizes the ECG, calculates heart rate, and streams data via CAN bus. As mentioned, for the validation of our system, we need a reference device. As reference, we used ECG chest strap that the subject has to wear on his skin. The sensor is called EKG Move and is produced by the company MovieSense. The third component is the real-time data logging device, Xeria 6810 from the company X3. The logger supports common automotive bus standards like CAN or FlexRay and dispatches data via Ethernet. So how do these components work together? We receive driving dynamics data like vehicle speed, steering angle, yaw rate, acceleration, and GPS coordinates, and also our capacitive ECG via CAN. The logger collects all bus data we are interested in and streams it to our PC. As mentioned, we get the data from our reference device via Bluetooth. The core of our framework is the Java-based sensor middleware XEffect. XEffect was developed at our research center for information systems and is now open source. XEffect manages data sources, data sinks, and data processors and allows online data processing. It's very easily to be expanded by new sensors or new algorithms that supports the rapid prototyping. Let's say glance at the software architecture. The picture shows the different components of our framework. On the one hand, we have two data sources, the Xeria logger and the MovieSense sensor. XEffect links the data sources to data sinks or data processors. In our case, we have two data sinks, the Unisense logger. Unisense logger stores all sensor data into a single data set using the Unisense data format. It was also developed at our research center. And this data sets allows the offline development of algorithms using MATLAB, for example. We also implemented a GPS logger that saves the GPS coordinates into Google Earth compatible file. To control the framework, we designed a graphical user interface that is displayed inside the car. The user interface was designed with focus on usability so that even unexperienced users can do test runs. Now take us a look at the results. Until now we did 5 test runs with an average drive time of 1 hour. We used a test track composed of urban streets, inter-urban streets, and highway. After the test runs, we compared the reference ECG with our capacitive ECG. More specifically, we compared the detected R peaks and classified the detections of the capacitive measurement into true positives, false positives, and false negatives. The classification allows the calculation of the sensitivity, also called hit rate, or the positive predictive value, also called precision rate. The capacitive ECG measurement shows very promising results. We reach a sensitivity up to 95.5% and a positive predictive value up to 92.6%. You can see that in comparison to the test RISE 1 and 2, the RISE 3 to 5 showed improved results. This is caused by a change in the measurement setup. To improve the contact to the subject and to reduce the influence of vehicle vibrations, we placed a compressible foam between the textile electrodes and the seat backrest. In addition to that, we are also able to identify a strong source of common mode noise in the car interior. For test drive 3 to 5, this was effectively shielded, which further improved our ECG signal-to-noise ratio. Now let us take a look at the influence of vehicle dynamics. This example shows the influence of this steering angle on the capacitive ECG signal. The driver steering movements mostly involve the upper body and can cause artifacts. For small steering movements, the baseline of the ECG signal changes, like you can see here in this picture. But bigger movements, for example, during parking, causes very strong artifacts and makes it difficult to detect R peaks. The next example shows the acceleration down direction. Especially the Z acceleration down, which captures road bumps, correlates strongly with artifacts in the ECG signal. Bumps in the road lead to a relative movement of the driver with the electrodes. This causes electrostatic charging and change in the coupling capacitance between body and electrodes. The picture shows an exemplary episode. Each artifact corresponds to a local Z acceleration maximum. With this information, we can now develop algorithms that estimate our signal quality and that detect artifacts to avoid misinformation. So what we have done is we developed a framework that allows the validation of physiological sensors or algorithms under realistic driving conditions. We are able to validate custom sensors by reference devices. We can analyze the influence of vehicle dynamics on signal quality. We can gather data, develop algorithms with this data, integrate and test them online. With our framework, we tested our capacitive ECG measurement. It shows really promising results. We reach a sensitivity up to 95.5% and precision rate up to 92.6%. What we want to do in the future is, of course, we want to do further test series to establish a database for statistically sound assessment of capacitive ECG measurement. Then we will develop algorithms that can estimate the ECG signal quality, and of course algorithms that can provide the driver's state. We also want to integrate additional physiological sensors, for example, in the steering wheel. This could be EDA measurement, skin temperature, or SpO2. And we want then to fusion all information from these multiple physiological sensors and estimate driver state for future assistance systems. This was my talk. I thank you very much for your attention.
So, thank you very much. Are there questions? Then I will start again. So, do you have some hints what you could gather with the ECG data? So you want to find out some special external behavior, how you could measure it with the ECG?
Only with the ECG it's difficult. We have to add additional sensors. And then we want to measure a stress level, for example. Or we want to measure if the driver falls asleep.
So that are additional signal which helps you to recognize some special
it's very difficult to get a driver state only from the ECG signal.
Yeah. And if I understood you right, so in a situation when there are hard accelerations or so, then your signal is distorted, and you have then to recognize this and to overlay it.
Yeah, to avoid misinformation.
Yeah,
that's right.
But then, especially in this situation, perhaps you want to have this signal.
Yes, of course. But that's only the first step.
Right. Yeah.
We do researches in the capacitive ECG measurement to improve the signal-to-noise ratio.
Yeah. Okay, are there further questions? Yeah, there is one.
I just wondered whether you took the back side of the seat. Why not taking more different locations for the electrode, so you would maybe get a higher difference between the potentials?
For example, where would you put it?
Maybe on the ground side of the seat, maybe, so you sit on it, maybe. So, and then you won't have this large motion when you brake or something.
We tried different positions, and it shows that the best position is in the back.
And would you say, how did you find out that it was the best? What was the criterion that you said it was the best on the back side?
We tried different positions and looked at the signal-to-noise ratio, and then decided.
Thank you.
So is there a further question? I don't see. So then thanks again to the author. We'll now go over to the technical papers, and the first one is presented from Levi from the Chiang University of Beijing, and his title is An Evaluation of Boosted Features for Vehicle Detection.
Today, I'm so glad to be here to give an oral presentation about my paper, and the title is An Evaluation of Boosted Features for Vehicle Detections. Here are the outlines. At first, I'd like to give the problem definition. Vehicle detection plays an important role in traffic surveillance systems, so I think it's necessary to evaluate the state-of-the-art detectors in real-world traffic data under different weathers, like cloudy, sunny, rainy, and so on. In our work, we focus on the frontal and the rear viewpoints with 30 degrees to minus 30 degrees yaw changes, and 5 degrees to 45 degrees pitch changes, just as so in the figure. Next, I will introduce the state-of-the-art features in other boost training algorithm. We do not investigate various training frameworks, but only focus on evaluating different weak features under other boost training algorithm, and then find the most effective and fast features for vehicle detection. Before introducing features, I think it is necessary to briefly introduce other boost training algorithms, which is fast, robust, and reliable in binary classification problems. And in this case, given a data set S, X are samples, Y are labels, the objective is to learn T reclassifiers from the feature pool F, and then form a final strong classifier. As for each weak classifier, first select a weak feature fx in F, and then train a weak classifier htx based on Fs. According to the classification results, update the sample weight. More specifically, if a sample is wrongly classified, its weight will be increased, and based on this, train the next weak classifiers. Finally, all the weak classifier will be formed a final strong classifier, just as this formulation. In order to better understand the procedure, I will show you a demo. In this case, different symbols represent for two classes, and each line is a classification surface generated by weak classifiers, which is learned from a weak feature. And then the weights of wrongly classified samples will be increased, and based on this, train the next weak classifiers. Finally, all the weak classifier will form the final strong classifiers. Next, I will introduce the existing state-of-the-art features. First is higher feature. Higher feature is widely used in face detection. Higher features consist of several adjacent rectangles with the same size. The feature value is the absolute difference of the sum of pixels in the white regions and the black ones. For effective training, higher features must be devised before training. The left figure is an illustration of higher feature, and the right ones are the first two hires selected by training. The second is joint sparse granular feature, JSGF for short. Are Boolean comparison of pairwise granulars, where granulars are square patches, just as shown in the left figure. And JSGF contains n pairs of granulars as a formulation show. And the right images are the first 6 JSGFs selected by training. The combination of the JSGF is learned by training rather than devised before training, and no requirement of adjacent patches, so it has more classification powers than higher feature. And furthermore, JSGF is Boolean values, not absolute difference. Therefore, it is invariant against brightness and contrast changes. Next is HOG. HOG has been proven to be effective for human detection. The feature is based on evaluating local histogram of image gradient orientations. And these are the first 2 HOGs selected by training. And eHog adds neighboring bins in the original HOG as new features to represent the edges as dominant orientations. Adaptive contour feature, ACF, it approximates the contours through a set of locations with similar gradients. For example, the link granulars LG in blue approximates the top contours of the vehicle, and the light blue ones approximates the bottom contour of the vehicle. and the two LG form a LGX. And the objective is to find a set of LGS to describe the contour of vehicles and use this to detect vehicle. The last one is associate pairing comparison feature, APCF. It contains pairing comparison of color, PCC, and pairing comparison of gradient, PCG. PCC is actually JSGF, while PCG is device for capturing the edge fragments, just as the middle figure showed. And the right ones show the first 6 APCF selected by training. And in these images, the red and green granulars is PCC, and blue and light blue ones is PCG. After brief introduction of boosted features, I will give the performance comparisons. Training data, we manually label 55,406 positive samples to train our vehicle detection, just as figure A showed. And as for taxing data, we collect 501 images, which cover the challenges of viewpoint changes, illumination changes, and partial occlusions. And another data set is from IEEE's public data set for event detection. All the taxing data is completely different with training data. And these are the ROC curves. The left image show the performance evaluations on our data set, and the right one is on IEEE's data set. In these images, record is detection rate, and FPPI is false alarms per images. And the bottom black light is hard feature, and the blue, green, and pink lights are ACF, EHawk, and Hawk, respectively. The top ones are APCF and JSGF. And APCF and JSGF outperform the other features. And which one is better and have better performance for vehicle detection? My answer is APCF, because it is more robust when there are location illumination changes. And the speed comparison are shown in this table. Although APCF has achieved the best performance, but is relative slower than JSGF. So we speed up APCF, and which is 20% faster, but with no performance loss. And the speed up APCF only use PCC in the course training stage, and both in the rest layers. Next, I will show you some demos. In these demos, APCF detectors are cooperated with particle filters, and they can process in real time, nearly 20 frames per second, on the size of 640 by 360. the weather of raining. Sunny. Okay. And finally is occlusion. How can we select effective features to improve the detection performance for vehicle detection? I have three main points. The first, in traffic surveillance, since the background are consistent, so color comparison-based features are effective to detect vehicles in these cases. Second, since there are viewpoint and scale changes of discriminative components of vehicles in our problem, so loose scale and range restriction are essential characteristics. Finally, besides the above factors, discriminative contour fragment approximation can further improve the performance. And thank you. Thanks for your attention. Any questions?
So, are there questions? There in the middle is one.
Thank you very much for this comparison. I know this is for a surveillance application. I was just wondering, how do you think this would perform on board of a car? So in a moving scene, do you think the classifier could be very tricked because of changing background, or how do you think the performance would be?
Sorry?
So these videos, this comparison you showed was with a static cameras, so surveillance applications, okay?
Fixed camera.
Fixed camera, yeah.
No. The cameras has slightly moved.
Yes, that's right, because of the wind or some other stuff. But if you put the camera on board of a vehicle, which would be moving much more, how do you think the performance would be? I mean, do you think the weak classifiers you presented would be effective enough?
On board
yeah.
camera, I think so. I think these features can work very well in the onboard camera. Because in the surveillance section, the viewpoint can change. The viewpoint change a lot, but on onboard cameras, in most situation is frontal and rear view. So I think might be easier.
Okay,
thank you.
Is there another question?
Thank you for the nice talk. I was just wondering that on one of your last slides you were saying you could speed up your feature detector to about 200 milliseconds.
Yeah.
Yes, and then you said your video is running at like frame rate of 30 frames per second, and I was just wondering how this was possible.
Can you?
Yes, you need like 200 milliseconds to compute the features.
Okay. These demos are combined with particle filter. So this time cost is for the whole image search. So, but the demos are cooperated with particle filter, which can reduce the loss of time.
How is this? How is this possible? I mean, you need to compute the features for every image, I guess.
But if a target is detected in last frame and we search the targets around the targets, the positions last frame, so we do not need to search all the windows. Based on this, we can speed up the.
Yes, but for picking up new ones, maybe, because you're initialized. You're not tracking all objects because new vehicles are entering the scene, and then you need to compute the features to detect those.
Sorry.
There are vehicles entering the scene, vehicles you are not yet tracking. So, in order to detect those vehicles, then you need to compute the features, right?
In our schemes, we divide the image into several parts, and in each frame, I use the whole window search in one part, and next frames, and in another part, we do not need to search the whole image.
Okay. Okay, thanks. I will talk to you later about that, maybe. Thanks.
You're welcome.
Okay, we want to thank again Sparse. So the next paper is from Dr. Robin Schubert. So it's a combined paper of Base Labs and the Chemnitz University of Technology, my own professorship. And the title is a Generalized Probabilistic Data Association for Vehicle Tracking Under Clutter.
Welcome to my presentation. We have seen from the previous presenter that if we talk about image classification, we always have things like false alarms, misdetections, and other not so nice effects. And I would like to show you how we can achieve a reliable vehicle tracking despite these disturbances. It's the last presentation before lunch, so I will try to save time by using the term GPDA for Generalized Probabilistic Data Association and the term PDA for Probabilistic Data Association. So my claims in this talk are, I would like to convince you of that current PDA algorithms are too restrictive for many practical problems that we are facing in the domain of intelligent vehicles, that the generalized PDA that we are proposing improves the tracking performance, and that it actually contains many of the known algorithms as special cases. And I would like to answer 3 questions in the presentation. What is vehicle tracking under clutter? How does GPDA solve the problem? And what are the benefits compared to the state of the art? Let's start with the first question. What is vehicle tracking under clutter? Most of you probably know the term vehicle tracking refers to the problem of estimating dynamic states of vehicles like position, velocity, and so on, but also to estimate the number of vehicles. And this is similar to the problem of estimating the existence of a certain vehicle, which is for many safety applications even more important than estimating the state accurately. So this is the one side, and the clutter on the other side denotes detections without a vehicle being existent, so it is also called false positives or false alarms. And vehicle tracking under clutter is all about extracting signals from noise. And I would like to illustrate that in a very simple example. I have here a test image from a red-green blindness. Just a short survey. Who of you is able to see a number in this picture? Should be around 90%, okay? This was easy. So here we are able to distinguish the signal from clutter because they have different colors, right? Unfortunately, our radar and LiDAR sensors are colorblind, so to say. So they are not able to distinguish the signal from the clutter without any additional processing. So in this image here, there is a letter hidden. Is anybody able to see it? Okay, let's try moving the pictures. Now anybody able to see a letter? What letter is it? An S, right. So what was the difference? The first image was static. And from the static image, we were not able to extract the signal, which was the letter in this case. The assumption behind vehicle tracking is that signal and clutter actually behave differently over time. And that's why we apply temporal filtering techniques that I will like to show you in this presentation. Okay, how does GPDA solve the problem? What is the approach? Let's consider a very simple example where we have only one track. A track is a hypothesis for an existing object, and we receive 3 observations from our sensor. And now what GPDA does is just simply enumerating all the possible data association hypotheses. So the first hypothesis would be that all of these 3 measurements are truly generated by an existing object. It could also be possible that only the first 2 measurements are true measurements and the third one is clutter. And then we can enumerate different hypotheses. It could also be possible that all the 3 observations that we have are actually clutter. So in this example, we have 8 different data association hypotheses. And the idea of GPDA, the GPDA filter, is to make a Gaussian mixture model. Oh. Sorry about that. So we have a Gaussian mixture model here, which combines all the hypotheses at one time step by calculating a weight mean of the posterior PDFs conditioned on this data association event. So this is, I think, a very familiar term here. It's the posterior PDF for a state conditioned on an association event A. And what we need here for the GPDA algorithm is this probability over here. Some problems with my computer. Okay, which is this probability over here, the probability of this data association event. And for that, what we need is a sensor model, like in standard Bayesian filtering. And for tracking, the sensor model consists of 2 aspects of cardinality and spatial distribution. So cardinality tells us, if we have our sensor, how many measurements do we typically receive per track. The clutter model tells us, if we have no object in front of us, how many clutter measurements do we expect per volume. And typically, but this is just an example, it's typically the clutter cardinality is modeled using a Poisson distribution. It could also be a uniform distribution. And the measurement cardinality is modeled by, in our case, by an arbitrary discrete distribution. And this is actually the main difference to the state of the art, because standard algorithms such as IPDA assume that we can at the maximum have one detection per track, but I will come to that difference later. The second aspect is the spatial distribution. Here, a typical assumption is that we model the spatial distribution of our object as a Gaussian and the clutter distribution as a uniform. But again, these are only examples. If you have a certain knowledge about the distribution of your clutter, which is not uniform, then you can also incorporate that knowledge into the GPDA filter. So in our example, we used the standard Gaussian distribution for the measurement spatial likelihood, a uniform distribution, so V is the hypervolume in our gate. We used a Poisson distribution for the clutter cardinality, where we modeled a clutter density. That is, this parameter lambda here is the expectation value for the number of clutter measurements per volume unit. So it's not the number of clutters, it's the clutter density. And for the measurement cardinality, we modeled the case that we have received no measurements from the object separately, and the case that we have 1, 2, 3, 4, whatever number of measurements as a uniform distribution until we reach a threshold. So we define a threshold, the maximum number of measurements per track. So in IPDA, this would be 1, the threshold. Okay, what are the benefits compared to the state of the art? When I'm talking about state of the art, I have to be more precise. I'm not talking about what is called single instance trackers like finite set statistic or approaches where we put all tracks into one common state space. This is not what we are focusing here on. I'm talking about multiple instance object trackers where for each track we use a separate filter, a separate state filter. And if we come back to our slides showing the measurement model, the likelihood model, we can actually derive many of the existence algorithms from this GPDA algorithm, and that's why we propose to call it generalized PDA. For example, if we want to use IPDA, which is integrated probabilistic data association, we would assume that we have a probability for 1 detection and a probability for 0 detections, but by definition, we exclude the cases where we have more than 1 detection per track. And this is, can be a problem for many applications where we are talking about high-resolution sensors, like laser scanners or like radars in the near field. And it can also be a problem for image classifiers, because usually we get several regions of interest for each vehicle. Normally there's done some clustering, that's why you never see these different hypotheses in the nice videos, but usually the classifier gives you a lot of detections for each vehicle. So we can derive IPDA from the generalized PDA by just setting the measurement cardinality to 1. Another example, many people are using SPRT, which is sequential probability ratio testing. It's one of the more simpler approaches to estimate the existence of an object. And this can also be seen in this framework of GPDA, again by using this cardinality likelihood. We have the detection probability for n is 1, and we have 1 minus the detection probability for a missed detection, so to say. And on the other side, we have a very simple clutter model, which ignores the spatial clutter distribution, but which models the cardinality also by having 1 clutter measurement with PF, the false alarm rate, and 0 clutter measurements by 1 minus the false alarm rate. So this is one of the most simple existence estimation techniques, and as you can see, we can embed it here in this framework of GPDA. Okay, for evaluation, we have done simulations and also tested it with real data. Here you see a simulation in a really high clutter scenario. We had a simulated vehicle which is moving here on the y-axis, and the vehicle is tracked, and you can see here that we have clutter and real measurements. Of course, the algorithm is not able to distinguish them. It's just for illustration purposes. And you see there are some slight differences in the tracking performance of the filters. But I would like to draw your attention to another aspect, which is the existence probability. And if we look at this scene that I just showed you, and we try to estimate the existence probability of this one track that we have, we see that actually IPDA, which is modeling that we can at the maximum have one measurement per track, is not able to correctly estimate the detection probability. We have here always a detection existence probability lower than 50%. And if we compare that to the GPDA, we can see that in this high clutter scenario, the performance is significantly better. We can see that even if we increase this maximum number of measurements per track from 1 to 2, so it's just a slight adaptation of this assumption, we have a significant improvement. And if we increase it further up to 20, the improvement is not so large anymore, but the first increasement is really significant. And on the other hand, I would like to show you a real scene with real data. I have a video showing you the classification results of an image classifier, only one short video. And you will see here, just as a disclaimer, many detections per vehicle. This is kind of unusual. If you see other videos, you see only one. This is due to the fact that often we have some kind of clustering behind, and here you see the results before any clustering. And this looks like that we have here 2 vehicles, and our classifier gives us a lot of different detections. And even if we do a clustering now, it may happen that we have more than one detection per vehicle. And our idea was here to analyze what happens if we are not clustering the detections at all, but directly give them to a multiple object tracking algorithm. This is possibly no practical use case because you would not want to give more than 20 measurements to a tracker, but we just wanted to evaluate the potential of GPDA. And the results are shown in the paper in detail. I would just show you one aspect. Again, I have here the existence probability for the first 100 milliseconds after the vehicle was detected for the first time. And you can see here that if you compare IPDA and GPDA for NS4, then even after one measurement, so this is where the 30 frames per second camera, so this is after the first image we received, the IPDA gives out an existence probability of about 73%, whereas GPDA with no more than 4 maximum detections per track gives 98% even after one time step. And this continues if we evaluate the tracking performance over time, that incorporating this assumption that one track may generate more than one detection, this really helps to improve the estimation of the existence probability. By the way, it also helps to increase the state estimation accuracy, but as I said before, often the existence probability is even more important. So that's why I'm focusing on that here. Another remark, I'm focusing here on IPDA and PDA algorithms for one object, just to make the presentation simpler. Of course, all the things can also be extended to a joint PDA, so JPDA, JIPDA, and so on. It's just as a remark. And with this slide, I'm coming to the end of my presentation. In time, as I think. I wanted to show you that GPDA loosens this one measurement per track assumption, and that we can have an improved performance with the GPDA filter, even if we only increase this maximum number of detections from 1 to 2. This was my main message, and now you have to take a difficult decision if you want to go to lunch or to ask any questions. In any case, I'm happy to answer them, and I thank you for your attention.
Okay, I think you are so quick, so we have time for 1 or 2 questions.
I think there to the left is one.
Yeah.
Thank you. This is very interesting, very good presentation, I think.
Thank you.
I have one last question. Normally we do after detection, we do the tracking, we always get a lot of these detections for one object. Normally we do clustering, always have to find some way to choose only one of them to update our tracker.
Mm-hmm.
Here you show that another possible, and I just want to know, how do you think the performance is this one? Your method here, is this much faster because I know data association, we do this always costs maybe some more time, but.
Okay, I try to answer what I understood.
Yeah.
The second question seemed to be about the processing time of the algorithm, right?
Yes. Do you think this is faster?
Yeah. Now, if you compare GPDA to IPDA, you have an increased complexity.
Yes.
I showed you the 8 hypothesis in the simple example. If you have only the assumption that you can at the maximum have 1 detection per track, then you have, for example, 4 hypotheses. Yeah, measurement 1, 2, 3, or
yes.
none at all. So this shows how the complexity is increased. Additionally, if you combine it with the joint variance with JPDA,
yeah.
it decreases again. But that's why I was repeating several times the fact that we don't need to increase this maximum number of detections to 20. It's already sufficient to increase it to 2, which does not really make the complexity explode.
Okay.
The first question was about the clustering, why we did not do that?
No, I think that's the only question.
Okay,
and
thank you.
2 is enough, or 4 is already enough for this, for
yeah.
the real-time application. For real-time application, 2 or 4 is already enough.
In our example, yes.
Okay.
I'm not sure if that is valid for all the problems in the world, but in our evaluation, this was the result.
Oh, thank you.
You're welcome.
Okay, is there another question?
Yes, Klaus Dietmeier from Ulm. I have a question regarding the how optimal the algorithm is. Can you prove that your general solution isn't optimal in a sense? Is that possible?
Well, I'm no mathematician. From my experience, it's always difficult to prove optimality for multi-object trackers. I've seen works where the joint JRPDA has been used and the things have been proven, but I have not made any analysis in that direction here concerning optimality.
Okay.
Because I see here due to this threshold, I see it more as a practical system, because in theory you would need really an infinite maximum number of detections per track in order to capture all situations. And here again we make a restriction. We have a threshold, let's say 2 or 4. And this cannot be optimal, so I see it more as a, let's say, practical approach to have a feasible PDA algorithm.
Okay, but you have to have a fixed number of detections in your algorithm. You must say beforehand it's 2 or... It's
no. I just define the maximum number of detections. Okay. So if I receive 2 measurements and my threshold is 10, then I still consider only these 2. So it's not that I assume how many measurements I will receive, but it's assume how many measurements at the maximum can be generated by one track. This is what this threshold says.
Okay. Thanks.
You're welcome.
Okay, I want to end the session and to thank again all the speakers and the contributors.
Thank you.
So, and I want also to announce the next session starts at 13:50 and we have no time for lunch.
All right, I just unplug the cable. Gracias.